Next we have example 2.9, and here we have to solve this initial value problem, this IVP, consisting of this differential equation and this initial condition. The equation is this: x sin by dx plus x square plus 1 times cos by dy equal to 0, and the initial condition is y of 1 equals pi divided by 2. So you can see that the equation is in variable separable form, so that's how we are going to proceed. So we start the solution by separating the variables of the given differential equation, and doing that we get this. So what do we do to separate variables? In this case we had to divide by x square plus 1 times sin y. Note carefully that x square plus 1 is never 0. For no real number x is it ever equal to 0. But sin y may be 0. In fact, y is the unknown function that we want to find, right? Which also satisfies this. So who knows, maybe the unknown function that will satisfy this equation is actually such that sin y is equal to 0. But say we assume that sin y is not 0. With that assumption only we can do this transformation. And when we do so and go through the necessary cancellations, this is how we get all the terms involving only x here, grouped here together with dx, and all the terms involving only y grouped together here with dy. X divided by x square plus 1 dx plus cos y divided by sin y dy equal to 0. And now we can integrate this, of course, because the variables have been separated. But we should not forget that condition, that all of these things are happening under the assumption that sin y is not equal to 0. So once we complete our task here, we have to go back to that assumption and investigate what we are missing. That is, then we should take sin y equal to 0 and see what we get from that. So next we go through the integration process. We integrate both sides of this equation. On the right side, we would normally get a constant, an arbitrary constant. But anticipating what we are going to get from these integrations, that is what the integrals ultimately are going to be, in what form they are going to appear, we have taken natural logarithm of the absolute value of C1, where C1 is some non-zero but arbitrary constant. We need this non-zeroness because ln of 0 is not defined, and we need the absolute value because natural logarithms of negative numbers are non-real complex numbers. Okay, so we want real number, that is why. So what do these integrals, or what do these integrations give you? What are the integrals? The first integral is 1/2 of natural logarithm of x square plus 1. I am not going into the details of how this is equal to this, okay, that you already know from calculus. Actually what happens is that you have to take 1 divided by 2 outside and multiply x by 2, so that the differential of x square plus 1 is what you get here, 2x dx, and then you do the integration, natural logarithm comes. Why are we not using absolute value here? That is because x square plus 1 is always positive, that is why. Here however, in the second integral, you can see that if you take the differential of sin y, you are going to get cos y dy. So this is also natural logarithm of, but sin y may be negative. The assumption that sin y is non-zero is there, okay, but still sin y may be negative. To prevent that, we take absolute value here. And on this side, of course, we have ln of mod C1. And then we multiply both sides by 2, obtaining ln of x square plus 1 plus 2 times ln of mod sin y equals 2 times ln of mod C1. And then you know logarithm property. The 2 will get inside and will become exponent. So that way we get sin square y. The moment we get square, there is no need for that absolute value. So that's why we simply write sin square y. and on this side also it becomes just C1 square. Actually that is because mod C1 square is equal to C1 square, that's why. And then further properties of logarithm, the sum of these two logarithms equals the logarithm of the product, x square plus 1 times sine square by, and on this side ln of C1 square. And then when you lift log from both sides, this is what you get, x square plus 1 times sine square by equals C1 square with what condition? Two conditions. The first is that sin y is not equal to 0, which is there with us in this part, and also C1 is not equal to 0. So this is a one parameter family of solutions of this equation, not exactly, well, for the original equation also it's the one parameter family, but are we losing something by assuming that sin y is not equal to 0? That is what we are next going to see. So we next write the above one parameter family of solutions. That means this one parameter family of solutions comes with the condition sin y not equal to 0. Now if sin y is equal to 0, then you know what y is. Y is then an integer multiple of pi, n pi, where n is any integer. And what are these? These are constant functions, where you can regard this as a function of x, where as x changes, y does not change, it stays n pi. Once you have chosen that n, then it becomes a constant function. All these constant functions are solutions of the original equation. How? Let us see that also. If y is n pi, where n is some integer, then sin y obviously is 0. What about, so sin y is 0 means this term vanishes. What about this term? Here the differential of y, which is dy dx times the differential of x, is 0 because the derivative is 0. We are talking about a constant function. So this also vanishes. That means yes, all these infinitely many constant functions are also solutions of the original equation. This one parameter family, however, does not have those functions. So in a sense, we have lost all these solutions. Now we have to also mention them, and luckily there is a way of incorporating these extra infinitely many solutions here itself by lifting those requirements that sin y has to be non-zero and C1 has to be non-zero. You just simply write this equation for the one parameter family without those restrictions. How does that incorporate these extra solutions into it? You see, say your y is one of these constant solutions. Say y is equal to pi. To be specific, so let me take y equal to pi. Then, is that available here? Well, it is available here with the choice C1 equal to 0. Actually, C1 equal to 0 takes care of all these functions. So we can regard this itself as the one parameter family of solutions of the original differential equation, where we did not, we no longer have this type of restrictions and everything has been taken into account. But that's of course not the end. We still have to find that specific C1 for which y of 1 will be equal to pi divided by 2. So we write like this, what I said just now. All these extra solutions can be included in our one parameter family if we write the one parameter family as this: x square plus 1 times sine square y is equal to c, where c is a non-negative arbitrary constant. By allowing c to be non-negative but not strictly positive, we have included those things because we can take c equal to 0. So all the y's for which sin y is equal to 0 are also included. And now in this family we are looking for that member which satisfies our initial condition. So we just put the values here. So x is equal to 1 and y is equal to pi divided by 2. So that gives us this equation which tells us that C should be 2 if that has to happen. So that means the solution to our IPP is this particular solution, x square plus 1 times sine square y is equal to 2. You note one thing carefully, that you haven't really got here immediately y as a function of x. Do not forget that thing which we discussed long ago or not so long ago. Whatever solutions we are going to get using these methods to these particular types of equations will be formal solutions. To know whether they are actual solutions, that is whether they give us explicit solutions, you have to work more. You have to see whether this relation really defines y as a function of x and whether that explicit function really is a solution to the original differential equation. But here that is not our aim. We just want to be more and more familiar with the methods themselves. These issues we will handle afterwards. So let me just end this video here itself. After this example, next week we are going to discuss homogeneous equations. These are equations of a particular type which are themselves not separable equations, but if we apply a particular transformation to them, then they turn into separable equations and then we can solve them. So next week we will see that. Until then, this is me, Lucifer from A Mathematical Group. Have a nice day.